All right, so we're going to talk about distributed caching, JCache, and more. So we all know hash map, and it's not thread safe. When we want to share the hash map in our application, we use concurrent, but it doesn't. All right, concurrent hash map, right? So now it's okay to share these entries. So what if we want to share the map across multiple JVMs running in the cluster? For this, wow. All right, so that's gonna be okay. So we use so we start an Hazelcast instance with a configuration, and then we say Hazelcast get map, and this gives you a Java util map that you already know from Java, and now you can share the entries across multiple JVMs. Just imagine you're building a web application and you want to share session information. So one Tomcat application might be storing the sessions, and if the Tomcat dies, another Tomcat instance can look up for the session and continue serving the session because we share the session information, right? Session ID and the session object. So I'll do a quick demo and you'll definitely get it. So it's easy.
Excuse me. When you're talking about maps on the cluster, are you talking about ACID maps? Are you talking about maps which have more relaxed nature? So if you have a map in a cluster, you guaranteed ACID conditions, or is it different? So what are the characteristics of the map?
Oh, okay. So the map that we're talking about is partitioned map. So if you have 10 million entries and 10 nodes, you're going to have 1 million on each node owning and some backup, right?
Well, I'm not actually asking about that. I'm asking when you retrieve it, however it's implemented or sharded or partitioned.
Right.
When I come back, am I guaranteed to get the right answer, or is there some amount of necessary relaxation because it's across a cluster?
Correct. I got it. Yeah. So when you do a map.put or map.get, we take the key, we figure out who owns that key. So that means we always go to the owner, right? So we go to the owner in JVM and do the operation there. It could be a read operation, map.get, or a write operation, and all these operations will happen on the owner first. So let's say this: if the network is stable, that means there is no network partitioning or split brain. We try to be 100% consistent. We go to the owner and read from the owner always. So the operations are going to be updates are going to be atomic at the owner, and backup will be taken sequentially, meaning the owner will send the update to the backup nodes, and so obviously, can we say the entire operation is atomic? No, because we're not stopping the world and saying, hey, I'm going to update the owner and the backup and make sure they have they don't see or read any different value. We don't do that. But when it comes to updating on the owner, it's atomic because we go to the owner and owner makes sure that the concurrency is taken care of at the owner level. So this is for the regular operations, like when you do a map.put, map.get, without any transactional boundary. So, but if you want transactional guarantee, then you say, hey, I want to use a transactional map. I'll start a transaction, I'll do my updates, and I'll commit. So that gives you extra guarantee in a way that so when you're in a transaction, we get the right locks and all that stuff, and when you commit, so regular transaction stuff. Yeah. Right. Okay. So, okay, let's do a quick demo, and you'll get the most of it. So when you unzip Hazelcast, you'll see something like this. So we have Management Center to manage the cluster. So we're going to see that. In the lib directory, we have all the Hazelcast jars. And this is the only jar you need, the Hazelcast all jar. Take that jar, put it into your class path, you're done. No dependency, we don't rely, or we don't use any other external JV jar. So single jar. So it's about 7 meg, single jar. But of course, if you let's say you want to use a client server mode, so you can run the server and then use the client jars to connect. Or if you're using Hibernate in your application, you can use Hazelcast as the Hibernate second level cache with these jars. Or if you're using J2EE and if you're using J2EE transactions and you want Hazelcast to participate in this transaction, you use the JCA. If you're using Spring, which is very common, then you use the Spring jar. But Hazelcast all contains everything. So just take that jar and forget about the rest. OK. So demo contains a console application that I built for demoing Hazelcast, actually. So let's see what it does first. So there's no trick. There's no complicated thing. So it says Java, please use this jar and start my console application. There's no other jar, anything. So it's a command line application. So I'm just going to start sh console sh. So we'll say there's only one member in the cluster, and it's me. This is my IP. This is my port. That's where I listen. And I'm gonna start the management center also, just to visualize the cluster. So it's fun. sh management center, or start management center, of course. Okay. All right. I will log in at admin, and no, thank you. Okay. So I see that I have only one member, and I have default map. So I'm just should I make it bigger? I'll make it bigger a little. So I'll put an entry first. Okay, so this guy is my man center. I don't need this, so it can stay here. m.put 1 and sf m.get. As you can see, I mean map.put and get, right? So there's nothing fancy. So, but I just want to show you that now. So this node has one entry owned, and there's no backup because there's no need for backup. So I'll start the second node. Sh console sh. Let's see what happens. So this guy will discover that guy, and they will form two-node cluster. So they used multicast. They figured out each other, and they joined. Now, if I look at the management center, remember that entry was here? It actually moved here, right? So it's a dynamic partitioning. So you have, I mean, the key was in one partition that was owned by this guy, but after the second guy, the partition is owned by the second guy. That's why it's there. And because there's one other node, we have also a backup on the other one, right? So it's very simple. So let's put more. Put many command will do it. I'll put 1,000 entries, and of course you'll see 1,000 and 1,000 here, 1,001 because we had another one also already. So, but I'll start the third one, and you'll see, of course, what do we expect? We want another guy to come here, and we'll see these guys like resharded again, but total will be the same. Yeah. So it will eventually become 1,001. We're not rushing for like taking all the backups. but so here also we're showing if there's an event happening, if there's any like event fire on this map, if there's any lock on any of these entries. So there's none yet. So okay, let's wait. Okay, so you see there's no like 330 anywhere here, because it's not like one node is the backup of the other. It's mostly more like these entries are actually here, sharded. So the reason is that when this guy dies, we don't have to rebalance again. It's already, the backup is already rebalanced. So so it's a Java map, Java util concurrent map, but we extended the map so that we can do more with it. Like we can lock the entries, we can lock the key one from here, and if I try to update from another one to Istanbul, I'm from Turkey, so I'm not able to because there's a lock on the key, so it's blocked right now. It will go through as soon as I unlock. Just watch the other one. So it just went through because this guy was waiting on the lock for the key one to complete the operation. So we unlocked it and it went through. So you can also listen for the entire map updates. You can say, I'm listening here. I just want to get informed for all the updates. If I do m.put, I don't know, to London. So this guy will get notified that a new entry is added by this guy with the key to and value in London. So basically, at this Java map, distributed Java map, which is partitioned across multiple JVMs, and you can lock the entries, individual entries in a map, and you can listen for the updates. Yes?
So I'm using something like Memcache,
yes,
which is kind of like a glorified distributed map. I'm effectively putting a value. That value gets serialized, stored in Memcache, and then when I retrieve it and deserialize it. Is that effectively what's going on here as well?
Basically, yes. But so Memcache is built to be key value only, with caching in mind only, and it's built as a single server, right? Single server, and there's no like if you start in multiple servers, they don't know each other, right? So if you have to use a proxy that will take care of like routing to the right Memcache server or migrating some of the data from here to here, right? So all that stuff has to be taken care of by a proxy. And there are proxy implementations available, like one is built by Facebook, I believe. But you have to go through a proxy to talk to the set of Memcache servers. Here, there's no such a thing. It's cluster nodes know each other. They're dynamically sharing the data, resharding the data, and failing back. So there's no need for a proxy in our case. So is that?
Yeah, I'm just.
Okay.
I mean, part of why I came here is I'm trying to get what like the fundamental different, like fundamental level, the difference between Hazelcast and something like.
If you go all the way down to key value, yes, it is exactly the same, right? So you're starting key value. In Memcache case, you have to serialize your key values into some byte array or string and then put it into Memcache. In Hazelcast case, because it is Java map, you pass an object to us, right? And then internally we serialize them to byte array and store eventually. So eventually it becomes the same, right? So either you do it or we do it, doesn't matter. Eventually will be byte array and stored on the server. Memcache is client server, right? So you have to have a client and a server. Hazelcast is a jar. That means you can start the Hazelcast server node inside your application. It doesn't have to be a client server, but you can make it client server too. So it just So Hazelcast embeddable, Memcache isn't embeddable. And it, as I said, it's a single server setup. This is multi-server and dynamic. Yes, please.
Due diligence with infrastructure is always a good idea, but so far this sounds great.
Thank you.
Okay. So I just have a question about security. If you're an enterprise setting, is this integrated with security mechanisms so it can go through some level of access control?
Right. So we have 3 levels. One on the wire that we can encrypt the entire communication between the nodes and the clients. So SSL is like very quick setup, for example, or we can use a symmetric encryption. So at the wire level, we can do that, and then after that, at the socket level, we can let you intercept the socket connections, and you can decide whether the connection is authorized or not. So let's say you're going to do a Kerberos lookup for that client before they can do anything. So client connects to the server, and you intercept that. We let you do that, of course, with that interface. And we pass you the socket. And you start exchanging data from client to server. And then you say, I don't like this guy. I'll shut down the socket. Or you say, that's good client. That's the second level. And the third one is entirely Java security framework. So you can say, so a client passes passes the credentials, and based on the credentials, on the server side, you can say, this guy can read this map, but can only and can write to that map, and can execute code for the other map. So you can define the entire read, write, execute. There are already built-in stuff like that. You can use the configuration, or you can just write your own login modules and everything yourself. So it's all 3 level. So security is a big feature for data grids. So that's another one. For example, Memcache versus Hazelcast. Like Memcache is probably 1% of Hazelcast when you look at the whole thing. But I'm not trying to. So Memcache is perfect for what it is. If it is what you need, what you want, then that's perfect for that. But if you care about security, if you care about dynamic clustering, if you care about this and that, then you consider Hazelcast. Redis and all that stuff, I love it.
Are there any requirements on the keys and values that be serializable?
Yes, they have to be serializable, or you have to provide us a serializer. So maybe the object is not serializable itself, but you tell us how this guy will be serialized. Yes, and serialization is the biggest part of this, the distributed computing to me, clustering, because the network is quite fast, like 10 gig is pretty damn fast. But usually your path to the network is pretty slow. Like because you go through a lot of concurrency blocks, and then you hit serialization. So all these are going to slow you down radically, and you should not. Before blaming the network, we should look into serialization points, serialization of the objects, and also the concurrency points we go through, like the queues and all these synchronized blocks. So yes. So Hazelcast started as a distributed data structures project. So, and Java Map is just one of them. So just same cluster, same jar. You can use Java blocking queue, and you can have a distributed queue. Like you can say, hey, I'm going to try to consume from the queue. And another guy can say, hey, I have a task to be, or I can offer a task into the queue, and this guy just took it and unprocessed, right? So you just imagine a Java util blocking queue, but distributed. So several JVMs can put into the queue, other JVMs can consume the queue. So The same, just like the maps, you can have multiple copies of the queue, of course, because you don't want to lose the queue if a node dies. So this is like a FIFO queue that we know. Yes.
So if you do a distributed queue, you've got several nodes, and you have a power failure, everything dies.
Right.
When it comes back up, is the queue returned or is it lost?
For all the data structures that we will be talking about, like map and queue and all that stuff, they're in memory. But there are two ways to make it persistent. One is that you can have a map store or queue store behind the queue that we will store the items into a persistent store like a database or something. Or in the coming version, we're going to have a hot restart. So that means everything you write into the queue maps will be flushed to the disk, only so that we can restart the whole cluster without losing any data in a super fast way. So, but that's coming soon. Yeah. So, so the whole when you just remember Hazelcast as an in-memory focused product. The other stuff is like for convenience, like, yeah, I don't want to lose the data, so I'll store somewhere else, things like that.
And there's only one queue? I mean, you're just saying queue.take.
Right. So this is my command line dummy application, and so the name of the queue is actually default right now. So you can have, you will have hundreds of maps and hundreds of queues. That's very expected. That's you create them ad hoc. You don't have to define them somewhere. You just say, Hazelcast, give me a queue named ABCD, and it will give it to you. Or give me a map with a class name or something. So yeah, yeah.
So that's how you reference the same map?
Right. Name of the queue or name of the map will be defining like which map you're looking at right now. And each map will have, or queue will have, a different property or different configuration. One map could be completely in memory with no backup. Another map could have two backups, one asynchronous, one synchronous, with a map store backing it, like completely different, right? So, for each map, you can have different characteristics: backup strategy, eviction strategy, and this is very expected. Okay, all right. So I'll go. Is there anything that you want me to try? Like I can. It's risky, I know, but I'll like taking risk. Like I can kill nodes and.
We could die.
Yeah.
I was going to say, well, what happens when you when the node crashes?
Okay.
I mean, how does it rebalance those backups?
Okay. So let's pick one node and then let's kill one. So this guy is the first guy. Let's kill the guy in the middle, who will tell me. So this is the third guy. Looks like this is the guy in the middle. So I'll kill this. Is that okay? Okay. This is gone. So we'll see that it will go back to 2, and we still have 1002, and it will catch up, and it will tell us 1002. So because we had the backup of that node, we don't lose data. The cluster will say, so okay, let's start from the beginning. One node starts and say, is there anybody here? It will say, there will be no answer, so it will say, I am the master, I'm the cluster. And then another guy will come in and say, ask the same question, is there anybody here? And I'll say, yeah, I'm here, come join me, and I'm the master. I will let that guy in, and I'll make the decision on which partitions that guy owns. Right? I'll say, all right, I'll give you some of the partitions. I'll migrate some of the data. All right, so we share now. And then the third guy comes in, asks the same question. I will answer only. I'll say, yes, we're here. Come join us, because I'm the master. The other guy will not say anything. So the master or the oldest member in the cluster will accept the new nodes, or make a decision on who's live or who's dead, or who owns what, right? So, and let's say one of the guys just died, and I'll say, so I'll receive information about the liveness of the nodes from everybody, and I'll eventually make a decision. I'll say, based on what I got from everybody, I declare that this guy is dead. Even if the guy is not dead, I declare that for the cluster, that guy's dead. Okay, and then rebalance the ownership of the partitions. So oldest member has this is peer-to-peer clustering. There's no like a master like a defined guy who's going to be master. It's more like whoever comes first will become the master. But eventually, when the oldest member dies, okay, whoever the oldest becomes the master. So everyone become that master eventually. It's a good thing. Yes.
The master dies and there's some kind of negotiation.
Yes, it's already defined. So while we're forming the cluster, everyone knows the entire cluster list, and everyone knows who comes next. So everyone will assume that the next guy will be promoted to become the master already. We already know, and the guy will say, "I am the master," and no one will question that. And can they question? Is there any case that they can question? Yes, if there's a network split, right? Then everything is messed up, right? So if there's a 10-node cluster, there's a network split, each cluster will say the other guys are dead, and there will be two masters because there are two clusters, and they will be working independently without knowing each other for a while, and Hazelcast will accept that by default. By default, Hazelcast choose to be, if you followed cap stuff, in case of partitioning, Hazelcast will choose to become available. So, and it will say, okay, we're going to keep running, we are available, even though maybe we're no longer consistent because we lost some of the nodes. This is the default behavior if you don't do anything. But you can set up quorums in a way that you can say, hey, Hazelcast cluster, if you lose more than 1/3 or 3 nodes, you should stop working because you're no longer consistent. So you should not serve any data. So if you set up quorums, you can adjust how consistent you want to be. But the default behavior is like, I am available. I give up on the consistency, basically. Because it's a cache, that's the most common use case for Hazelcast kind of stuff. But if there are cases where you use Hazelcast as like an in-memory database, it's like a system of record. For those cases, you say, no, I won't give up on consistency. If I lose 1/3 of the cluster, no operation. I don't accept anything because to me, this cluster is not consistent. Okay.
Is it self-healing?
Oh yeah. So we talked about the split, right? So the split happened, and then they kept running, and then of course the network guys will figure out the problem. They will fix it in hopefully short amount of time. So during that time, actually, Hazelcast master guys are actually still searching for the other guys, saying like, they're going to say, or they're going to think like, is it possible that I was part of a bigger cluster and then I got split? Right? They will always question every 5 minutes. That's the default value, but you can change it. Every 5 minutes, they will say, okay, maybe I was part of a bigger one. Eventually, when the problem is fixed, they will ping each other and they will say, oh, yeah, we were part of a bigger one. Looks like there's a split. So now we have to merge. If there's when they're pinging each other, they pass how many nodes they have, and smaller cluster will merge to the bigger one. If they're the exact same, then the that there's an easy algorithm to like define who's going to join the join. So when they merge, of course, each can have the exact same entries, right? Like same exact map with same exact keys, with very different values. So now we have to merge them, which is super ugly. So Hazelcast has built-in merge policies. You can use any one of them, but you can build your own too. In that case, there's an interface that says merge policy. We pass you two values with metadata like version and update time and all that stuff, and then the values you make a decision on the final value of the key. But as I said, it's already a mess. So I don't think this is like a best effort thing, right? Does it entirely solve this problem? No, it doesn't, because the biggest problem here is that yes, we can merge these existing ones, but we have no idea about the deleted ones. So there are entries that are deleted, and we have no clue. So it's just it's a best effort merge.
Yes. So if there's a cache, maybe one of the most efficient policies would be just deleting conflicting keys.
Correct. Yes. If there's a cache, delete the existing ones. Yes.
When you have 10 peer-to-peer nodes, as a client, which one are you getting to? Which one do you go to? So if there's 10 IPs that are serving out this cluster,
Yeah.
which one do I talk to as a client on the outside of that?
Okay. Yeah. Okay. So this application that I showed you obviously was an embedded application, right? Just like you could have taken that jar and put it into your web application, and the server would start inside the application, and then servers are talking to each other, right? So there's no client really. So servers are also clients in this case. But it's very possible that you can have as a cluster, and you're using a client API to talk to the cluster. So in this case, you pass at least one of the IPs just to get started, just to connect to the cluster. And as soon as the guy is connected, actually the client will just fetch all the IPs and also the partition table. So meaning who owns what, right? So and then client actually knows for a given key, like map.put or map.get, the key, it will just do the exact same thing. The client will say, all right, this key belongs to this partition, which belongs to that guy, so I'm just going to use that connection to go to that guy. So same logic. So the clients are by default smart because they know where to go. But let's say you have thousands of them, then smart is not good because you don't want to have thousands of them connecting to every node. In this case, you have to use a dummy client which connects to only one guy and does every operation through that guy. So by default, it's the smart, so it knows where to go. Yes.
Suppose I've got very heavy applications doing a lot of processing. It has to be very asynchronous. And it's doing these computations, and it has to get 3 different answers before the next stage of processing can take place. So it has to compute A and B and C. Okay, there's different ways to do this, but could I use your system like to put the results in a map, and then could I have a client in a very lightweight fashion say, look, I'm just here and I'm waiting and not really doing anything until I see these 3 keys show up. And when these 3 keys show up, then I know I've got all my futures. I'm going to do this processing.
Good one. No, there is no. No. You.
I know it's a hard one.
Yeah.
It seems like if I could think that way, it gives me a very simple mental model at least.
There's no implementation like that, but so we have a data structure named multimap, one key multi-value.
That's
Yeah.
Three separate things, like waiting for them to all show.
Right.
It's synchronization, basically, right? But not at thread level, but at the key level.
Right. No, definitely not. Okay, let me think.
You couldn't set up a listener?
But you're listening for 3 different things to happen, and you have to be notified until after the 3rd thing completed. Which is, I think it's a good use case, and maybe we should work on that. But what is it?
The stateful listener.
Yeah, it's a like it's a conditional, actually even conditional listener, right? Like that there's a condition for the
I think
fire
my
up.
question included
Yeah.
lightweight, because I know
Right.
I can implement it, but I can do a heavyweight implementation that won't scale. But if the
Right.
infrastructure supported it, then it's lightweight enough, I can actually use it. And then
Right.
it might make a lot of processing
So-
much simpler.
So here's what I would do. So there's a feature called entry processor in Hazelcast or JCache, where you can send. Let's say there's an entry. So it works with a key. Let's say there's a computation ID or process ID that all 3 of them maps to, and after each one of them is done, they will send an entry processor to say I'm done, right? So you'll pass the process ID as the key, and they will go to the same node and mark the completion. And after each completion, you can say, oh, I got 2 of them done. Now I'm the 3rd guy. That means I have to fire an event. So, but you have to build that. It's not part of the thing, but with the entry processor, you can. I'll talk more about the entry processor. Let's.
Yeah, but that seems reasonable.
Yeah. So let's. Where is that thing? Here's my presentation.
Yeah.
Oh, it did. Okay. Okay. All right. Start again. There's something funky about this thing, but maybe. Okay. I don't think this will work. All right, now it works. Okay. So it's a single jar, no dependency, Maven friendly. Just get it from Maven. It's very quick. We talked about partitioning. So when you start the cluster, you say I'm going to have X number of partitions, and it's usually going to be hundreds, even thousands, depending on the data size and cluster size. So each key will fall into one of these partitions. So we're going to hash the key and then mark with the partition key, and we'll find the partition ID for that key. So that means as long as the keys are the same, we'll come up with the same partition ID. And then and every node in the cluster, even the clients, know which partition is owned by which member. And then we're going to route the request to that guy. So Hazelcast can be embedded into the application. This is a JVM. Your application, Java API, and Hazelcast node inside the same JVM. It's embedded. Or, as we talked, you can have a cluster of Hazelcast servers, and you can use a Java, .NET, or C++ client to talk to this cluster, right? And in each case, the API is exactly the same. I mean, you can start as an embedded cluster, and later on you can say, oh, I don't like embedding Hazelcast server into my application. You just can change the way you get the instance. Everything else will be the same. The way you get the map, the way you talk to map and queues and everything will be the same. So now, if you put this code into your JUnit test, you're starting 2-node server with 1 client. That will compile and run. This is perfect code. There's nothing wrong. So in a JVM, you can have 5-node cluster, and you can do your assertions in a JUnit test. So which is very convenient, actually. That's how we do a lot of our tests too. So it's thread safe. You don't have to synchronize on anything to do anything. And as I said, multiple instances can be started on the same JVM. And we do rely on serialization. So optimize the serialization crazy. Use either Hazelcast Java data serializable, or we have many different serialization mechanism, or you can use the one that you love, like Cryo or Protobuf, anything you like. Just make sure you optimize the serialization. It's the most costly thing in distributed data. You can listen for the membership events. You can say, hey, who joined, who left, or get a set of members with an API. So as I said, Hazelcast get map, name of the map is like pointing to the same map, right? We do support generics and everything. Of course, we love atomic operations like putIf absent. It's very convenient. Multimap is one key multi-value data structure. So when you do a get, you get a collection, and you can remove one item from the collection. Queue is Java util blocking queue that you already know. You say, hey guys, give me a queue named tasks. All timed operations are supported. It's very simple. There's nothing, I don't know, super simple stuff. Locking. Let's say you want only one JVM to do a certain thing. And for that, you have to have a lock, a cluster-wide lock. So you can either use the Java concurrent lock interface like this, or you can have a map and use the lock API for that map. So what you're locking is this particular entry, not the entire map or all the keys, all the same keys. Just this key in this map you're locking. All right, so you can, the topic is like a JMS kind of topic, right? Like pops up stuff, multiple publisher, multiple subscribers. So this is perfect code. You say, hey, Hazelcast, give me a topic, and I'm listening for, and I also want to publish something. So whoever is listening will be getting that message right here. On message, you'll get the message and you'll execute the message. So, what we're saying is like, hey, if you already have the cluster, if you already have maps and queues, do you really need an ActiveMQ or a JMS server to do all that stuff? Usually not. Like, we're not trying to replace them. But 90% of the time, we think Hazelcast queues and maps or topics will be what you need, basically. Events, we saw at the demo. You can add an entry listener, and you can listen for the updates. Hazelcast will notify you if there's an update in a map, update in a queue, update in any data structure. Transaction, we do support one-phase or two-phase commit. So basically, you have to get a transactional map or queue, and then you begin the transaction. You do your stuff, and then you commit. Something goes wrong, you roll back, just like other transactional stuff. Yes. Executor service is Java util executor service, concurrent executor service. So basically, your tasks or runnables are going to be running somewhere in the cluster, not locally anymore. So you say, here's my task. I want this task to run on this member, or all of these members, or I want this task to run on this key. So you're just saying, Hazelcast, just go to the owner of this key. Run there. Why? Because you have your data there, and you know that. So of course you can say, hey, map.key set or values, and you can iterate everything. If you have 10 million or 100 million, it will take quite a long time. And also, you don't want to bring everything to the caller, right? So let's say this is the value that we are storing, and we want to find active customers with age less than 30 or something. You say, hey, give me the map. You can add indexes just like you add indexes in database. And then you say map.values, and in SQL predicate, you say active and age less than or equal to 30. So the way this will work is like the query will go to every node in the cluster and only focus on the locally stored data on data and query that data there on each node, right? And then results are going to be sent back to the caller, and the caller will put together all these results, right? So if there's an index, of course, it's beautiful because we don't have to iterate on the owner node. We just can say, give me the values for that index. Super good. So with the Hazelcast architecture, so this is, so at the very bottom, we have the socket, right? The TCP/IP socket that we're always listening, or multicast socket that we're trying to discover. But so multicast is only for discovery. After discovery, we don't care about multicast. Everything is unicast. Everything is TCP/IP. So that's so if you're running your application on Amazon EC2, for example, multicast is not supported there. So we have three discovery mechanisms. One, multicast that we show at the demo, right? I use multicast by default. Super easy for development. The second one is TCP/IP, which is you're going to list the IPs of the nodes. You don't have to list the whole thing. You just have to tell us some of them that are going to be available, right? So we're going to join the cluster over those known set of IPs. The third method is the AWS, Amazon Web Services. So you give us Amazon information, login information, and we're going to scan all your nodes and query based on tags that you set and everything, and we're going to join the cluster automatically. You don't have to list the IPs or anything like that. Hazelcast will figure out the nodes running in your Amazon cluster. So this is networking with cluster management. So they're going to find each other. They're going to form a cluster. They're going to send heartbeats to each other and all that stuff. That's here. And on top we have the partition management that has nothing to do with any of that stuff, which is like who's going to own which partition, who's going to be the replica, and all that stuff is taken care of here without any application-specific logic. And on the node engine, we do take care of the invocations, and when you do a map.put, you're doing a distributed invocation, right? Because the invocation will take place somewhere else in the cluster. Or when you do a queue.take, which is like wait notified stuff, right? So you're waiting to be notified. That kind of stuff is taken care of by the node engine, and there's a low-level service API for those, and everything is built on top of that. So just like we built map, queue, and MapReduce, and atomics, and aggregations, and everything with this API, you can build your own distributed data structures with this API. So if you have anything, like let's say there's a data structure that you really want to build, which is very specific to your case, and we don't have it, right? And you can use this API and build your own stuff. Yes, and of course this is like a server, and on the client side we have a network protocol for the client and implementations, Java, C++, and C# implementations right now. If you want to have two different clusters in two different regions, and if you want them to like replicate to each other, you use one replication. If you care about security, you use the security framework. If you care about no GC, like let's say you're storing like 100 gig per JVM, which means like crazy amount of data per JVM that's subject to GC. And right now it's almost, it's definitely going to pause the JVM for several seconds. So if you care about latency, you can use the off-heap storage so that we will store your keys and values, everything off the heap. JVM has no information about that, so that means it's not subject to GC. So no major GC will happen. So the management API, we have JMX and regular Java API for managing the nodes and cluster. So this is basically how it's built. All the blue ones are enterprise kind of stuff, and all the rest is open source Apache and good stuff. So Jcache is a new spec for caching in Java. It's finalized recently, and every big container or every big framework will eventually have it. Spring already has it. J2, Java E 8 will have it. So basically, don't use. The idea is that you should be no longer using cache or any of all the APIs anymore. You just use the standard Java caching API. It's very similar to map with events and computation. We talked about interprocessor. That's what it is, and integration. So there are several vendors implementing this, of course. We are one of the first ones, which is very good. And our CEO, Greg Locke, is actually one of the co-author of the spec. So, all right, so this guy's already implemented Jcache. Many other containers will be also doing that. I think the other one would be Tommy Tribe is another one that's supporting Jcache. All right, so Jcache cache API is basically you get a provider that creates the manager that creates the caches. That's basically what it is. Okay, so it's very simple API. So provider could be Hazelcast provider, could be coherence provider, or could be local provider, distributed provider, whatever. So you're gonna say caching, give me a caching provider, and then you're gonna get a manager, and manager will give you caches. The beauty here is that it's now standard, right? So tomorrow you can switch from one vendor to another one. You don't have to change the code. And your developers don't have to learn new API. It's part of the Java spec. So there are beautiful things like, hey, cache the whole result, right? So just run this computation, use this key, and cache the result. So if I call the method again, don't run it. Just return from the cache. It's beautiful. You can persist the cache somewhere else with these interfaces, right? Cache loader, cache writer. So you talk to the cache, you do a cache.put, and cache will be using your implementation of the cache writer to store the entry into, let's say, a database. Let's say an OSQL or whatever. So, and whenever you try to get, if the key is not in the cache, it will load it. It will ask you to load it, actually, right? So you have to write the code to load it back, because we don't know where you want to store all that stuff. So there are like JPA, like pre-built loaders and writers already for Mongo, for JPA, and all that stuff. But I'm sure there will be more. So the basic idea is that like you're going to have multiple JVMs, multiple applications. And you probably will be talking to many data stores, like MySQL, Oracle, and then some NoSQL, and some maybe Search, Elastic, or something, Solr. So eventually, You can either talk to every one of them separately yourself, right? From the application, you can talk to them. Or you can say, I'm going to have different maps for those, and I want this caching layer to talk to my data sources. So if the map name is customers, it will be written to relational database. If it is logs, it will be written to NoSQL because it's logs and not transactional. If it is something text, it will be written to Elasticsearch or Solr. So you have the operational data store in between of the application and the database or data store. So JCache is beautiful, but it's not done. We still want asynchronous API, query mechanism, and transactions. So they're still working on it. So let's work on a scenario. So this is my final stuff. So like biggest thing, and then we're done. So let's say we want to remove an order from a customer object. We have customers map. We say, and let's say business requires that we lock the entry because we don't want anybody else to do anything when we're updating the entry. Let's say it doesn't have to be like that because the operations are atomic already. But let's say the business requires that. So you lock the entry, the customer ID, and you get the value, you change the value, and you put it back, and you unlock. Looks good. So I got the customer, I changed the customer and put it back with the proper locks. It looks good, but this is very bad because it won't perform well. What you're doing is actually with the backups, let's say we have one backup only, 2 operation here, 2 operation here, another 2 here. It's like 7 operations just to get this done. 7 distributed operations to get this done. This is horrible. So can we make it better? Can we make it more efficient? Any suggestion? How can we optimize this? Yeah. Right. Executor service. You can create a callable. And you can say, hey, it's partition aware. What you're saying, hey, Hazelcast, take this callable and go to the partition ID, partition key, customer ID, and then run this code right there. Why? Because your entry is there. And that way, some of the operations will be local, right? The owner part will be local. The backup will not be. The get will be definitely local, is to here, right? Put it back like owner part will be, right? So it's still from 7 to 4, pretty good, but still not perfect. Can we make this better? So if with the API you're going to say, Hazelcast get executor service, you create the task, you submit, you get the value. So this is how you end up implementing it, right? So can we make it better? Yes, we can, with the entry processor. So entry processor says, I can take your code and guarantee that I'm going to run your process method with an implicit lock on the key. So you don't have to, you can ignore the key, ignore the locks, right? Because I'm going to give you implicit lock already. And I'm going to guarantee that when I'm running this, the entry will not be moving one JVM to the other. So then, until it's processed fully, it's all yours. The entry belongs to you. Just do whatever you want to do. So which is perfect because now I can get rid of the locks, right? So it's already given me the implicit locks. So they're gone. Yes?
So the other clients see the previous value in that, for that key while you're still processing?
Yes. So you're going to read the alt committed value. But so it's always the committed, so it's like a committed read, yeah, or read committed. So okay, so this is beautiful because no more locks. So this is already giving me implicit lock, and it's already providing me the entry. I don't have to do a map.get also. Just like here it is. I know that you came for the key. Here it is. So entry belongs to you. Do whatever you want to do, and get out. So that means one operation to the owner, and then I'm gonna be done there. But of course, I now have to take care of the what? I have to take care of the backup. So backup is also beautiful because now I can run the same operation on the backup, but I don't have to, because let's say the process is a little more complicated. Let's say the process was like sending an email and then doing some updates on the database and then changing the entry and then returning. And you really don't want to do the same thing on the backup, right? You don't want to send the email again, at least, right? For that purpose, it says like, hey, give me an entry processor. It could be, that means it could be different. So it could be a partial implementation of that, just to change the value. Another benefit of this is like, in the previous example, you bring the value to the caller. So value could be big. Here, there's no value going on. Like it's already, you go to the value with the very little information, just order ID that you want to delete. So it's way smaller data moves, and you go to the data and you execute right there and you get out. That's.
Did I miss how did this piece of computation get to where the data is?
Okay, so I'll tell you. Okay, okay. First, you already implemented this process, interprocessor, okay, which is serializable and all that. But when you call it, you say this: hey, give me the map. Here's my delete order interprocessor. Hazelcast, execute this on the key. So
Okay, so it does the lookup here and
yeah.
sends it.
Yeah, and then runs there. So that's the entire thing. So now it's definitely one operation on the server and a small one on the backup. So that's the most optimal. So now just imagine a big object. Let's say a game object, which is huge. You don't want to bring the whole game object and just add something or change something, do a delta update and put it back. You really want to just go to the big game object and do the changes right there and get out. This is way more efficient. All right, this is basically what it is. I hope you enjoyed it, or it wasn't that boring. Awesome. Thank you so much.